When you strap into a roller coaster, there's this very specific, like, physical logic to the whole ride.
Oh, absolutely. The anticipation.
Right. You feel that slow, mechanical click, click, click of the ascent.
Yeah.
You're fighting gravity, right? You're moving strictly upward. You know exactly where you are climbing.
Yeah, you're locked into that path.
Exactly. And then eventually you know where you're plummeting, where, gravity takes over and you're just in a free fall. But the most defining moment of the entire experience, at least for me, is that stomach-dropping, kind of agonizing fraction of a second, right at the peak.
A absolute top.
Yeah. The moment you aren't climbing anymore, but you haven't quite started falling yet. You were just momentarily suspended.
It's a moment of absolute equilibrium. And in mathematical theory, that exact moment of suspension, where the system is neither increasing nor decreasing, that's known as a critical turning point.
And that brings us to the mission for today. Welcome to the deep dive. Today we're decoding a specific piece of mathematical theory. It's increasing and decreasing monotonic intervals.
Which I know sounds like a very dry calculus lesson.
Right, it totally does. But stick with us, because we are going to explore how this one mathematical concept, this behavior of a system as it climbs, falls, or stalls, acts as the hidden engine driving, well, basically the whole world around you.
It really is everywhere once you know what to look for.
Exactly. We're unpacking the mechanics behind aerospace engineering, the electronics charging in your pocket right now, and even the massive machine learning architectures that are shaping the future.
So if we strip away the jargon, the foundational concept is actually quite elegant. Think of a continuous function mapping a relationship. So you have an input producing an output over time.
Okay, an input and an output, got it.
Right. And we are looking at the first derivative of that function, which mathematicians write as f prime of x. And really, all that derivative is doing is measuring the rate of change.
Just how fast something is changing.
Exactly. So when that rate of change is greater than 0, the output is scaling upward monotonically.
So we're talking about a strictly increasing interval.
Right.
Just like that roller coaster climbing the track.
Yeah.
As time moves forward, the altitude only goes up.
Yes. The output continues to climb as the input progresses, but conversely, when that first derivative is less than 0, the output decays monotonically. It's strictly decreasing.
The big drop on the ride.
Exactly. But the really compelling part, the part that engineers obsess over, is finding the boundaries between those two states.
The transition points.
Right. To find where a monotonic window begins or ends, we have to look for the real roots of the equation. So the exact places where the first derivative, f prime of x, equals exactly 0.
The peak of the roller coaster, that single agonizing moment of suspension.
Yeah, those real roots represent state transitions. It's a mathematical boundary where a system fundamentally changes its directional trajectory.
But, why does an engineer actually care about finding exactly where that derivative equals 0? Outside of a textbook, what happens if you miscalculate that peak?
Well, it can be disastrous.
Right, because in the physical world, hitting that mathematical ceiling at the wrong speed can literally tear a machine apart. Let's look at how this plays out in aerospace engineering, specifically during a rocket launch.
Yeah, a rocket launch is essentially this massive, highly controlled exercise in managing aerodynamic stress.
Because it's pushing through the atmosphere so fast.
Exactly. During the ascent, the vehicle encounters loads that are defined by something called dynamic pressure, which engineers denote with the letter Q. And the models calculate this using two main things: atmospheric density and the square of the rocket's velocity.
Okay, wait, let me stop you there. If the rocket is climbing higher into the atmosphere, the air is getting thinner, right?
The density is dropping.
So shouldn't the physical pressure on the rocket be going down, not up? If the air is thinner, it should be easier to push through.
You would think so, but you have to look at the velocity term in the equation. And remember, that term is squared.
Oh, right, squared.
Think about, sticking your hand out the window of a car moving at 30 miles per hour. You feel some wind resistance, right?
So it pushes your hand back a bit.
But if the car accelerates to 60 miles per hour, the resistance doesn't just double. Because it's squared, it quadruples.
Oh, wow, okay.
That exponential scaling of velocity is what the rocket is fighting. So from the moment of liftoff, the exponential acceleration of the rocket's speed completely overpowers the linear drop in atmospheric density.
I see. So even though the air is getting thinner, the vehicle is punching through it so much faster that the aerodynamic load on the structural frame is, well, it's strictly increasing.
Exactly. The time derivative of dynamic pressure dq over dt remains greater than 0. We are in a strict interval of increase.
Right.
But structural materials, things like aluminum or carbon composite, they can only handle so much physical load before they buckle. The aerodynamic load scales upward monotonically until it hits a critical boundary.
The moment the derivative hits zero, when dq over dt equals zero.
Yes. In aerospace, they call this exact turning point max Q, maximum dynamic pressure.
Max Q. You hear them say that on rocket launch broadcasts all the time.
You do, because it is the physical moment where the battle between the exponential velocity and the decaying atmospheric density reaches its absolute peak intensity.
It's the top of the roller coaster, but with, like, millions of pounds of thrust behind it.
Exactly.
So if engineers don't respect that specific mathematical moment, what actually happens?
Well, the vehicle experiences catastrophic structural failure. I mean, it breaks apart.
Oh, wow.
Yeah. To survive that transition, flight computers are explicitly programmed to throttle down the main engines right as the vehicle approaches the max Q boundary.
They intentionally slow down.
They reduce the thrust, yeah, just to ride out the peak aerodynamic stress safely.
That is wild. They are literally managing the calculus in real time.
Right.
And then once they cross that boundary, they enter the interval of decrease. So dq over dt is less than zero.
Exactly. Post-max Q, the vehicle leaves the dense lower atmosphere and enters the near vacuum of space.
Where there's basically no air.
Right. At that altitude, density drops so close to zero that the velocity squared term, it just no longer matters. Aerodynamic drag decreases rapidly, even though the rocket is accelerating to orbital speeds.
So the structural load is now on a monotonic interval of strict decrease.
Spot on.
It's just so crazy to think about. A rocket launch feels so chaotic, right? It's basically a controlled explosion pushing a skyscraper into space. Yet underneath all that fire and vibration, it's just following this incredibly rigid mathematical sequence. Increase, critical turning point, decrease.
It really is. The physical reality is entirely bound by these continuous mathematical intervals.
Okay, so it's a massive macro level application. But I want to pivot because we don't have to look at orbital rockets to see this at play.
No, not at all.
The exact same framework dictates quiet, microscopic processes.
Yeah.
Because if aerodynamic pressure pushing on a hull follows this math, so does electrical pressure pushing electrons. Let's talk about a basic RC circuit, a resistor-capacitor loop. Something as simple as the charger for a laptop or a phone.
It's a great example. The transient charging behavior of a capacitor perfectly models these intervals.
How so?
Well, when you plug a device into a DC power source, the voltage across the capacitor doesn't just instantly appear. It's not magic. It climbs according to a very specific decay factor based on time, resistance, and capacitance.
Okay.
And if we take the time derivative of that voltage, we see the rate of change is always a positive value.
Meaning the voltage is locked on a strict uphill climb. It's a strictly increasing monotonic interval.
Right. It approaches its full capacity asymptotically, getting closer and closer without ever mathematically crossing the finish line, but it is always climbing.
So the electrical pressure building up in the system is increasing monotonically, but we have to look at the other side of the system too, right?
Yeah.
The current.
Exactly. The loop current is tied to how fast that voltage is changing. And if we take the derivative of the current, the result is actually strictly negative.
So the current is on a monotonic interval of strict decrease. It's going down. But what is the physical mechanism causing that? Like, why does the flow of electricity just drop off on its own?
It comes down to something called electron crowding on the capacitor's plates.
Electron crowding.
Yeah. As the voltage pushes electrons onto the plate, those electrons create a negative charge. And because like charges repel, the electrons that are already on the plate physically push back against any new electrons trying to join them.
Oh, so the fuller the battery gets, the harder it fights back against the charger.
That's exactly it. The resistance to new charge grows stronger with every passing millisecond. And because that physical pushback is increasing, the actual flow of electrons, the current, well, it chokes itself off. It drops steadily, decaying toward a 0 amp steady state.
That is such an aha moment. Because when you plug in your phone, you're basically initiating this perfectly choreographed event.
It really is a dance.
Right. Two mathematically opposite intervals are happening simultaneously. The voltage, the electrical pressure, is on a strictly increasing interval. But at the exact same moment, the current, the physical flow of those electrons, is locked on a strictly decreasing interval.
It is the exact same fundamental math that dictates a rocket surviving the atmosphere, just applied to the flow of charge across a dielectric barrier instead of, a titanium hull.
Mind-blowing. Okay, so we've tracked these intervals through Physical aerodynamics and electrical flow. Both of those are tangible things. You can measure pressure, you can measure current.
Sure.
But what happens when the terrain isn't physical or electrical at all? Like what happens when the landscape is purely abstract data?
Yeah.
Because we found in our research for this deep dive, the exact same math dictates how artificial intelligence architectures learn.
Yeah, this is where it gets really abstract, but incredibly important. Machine learning relies heavily on optimization via something called gradient descent.
Gradient descent.
Right. See, when an AI model is training, it isn't thinking in the human sense. It is just trying to minimize an analytical objective function known as the loss function.
And a loss function is essentially the algorithm's error rate, right?
Pretty much. The higher the loss, the worse the AI is at its job. So the entire goal of training is to drive that error down as close to zero as possible.
So to achieve that, the training architecture has to maintain an interval of strict decrease.
Exactly. The optimizers compute the gradient, which is basically the multidimensional slope of the loss surface, and then they update the model's internal weights in the exact opposite direction. They are constantly desperately looking for a negative derivative.
Let's try to visualize this for everyone. Instead of a standard 2D graph, imagine dropping a marble into this massive, uneven, multi-dimensional bowl.
Okay, I like that analogy.
The marble represents the AI model, right?
Great.
And its only goal is to roll to the absolute lowest point in the bowl, which is the minimum error. Gravity pulls the marble down the slope. As long as the marble is rolling downward, it is in a strictly decreasing loss interval.
That's a perfect way to picture it. The AI is continuously evaluating the slope beneath it. The size of the step the algorithm takes to update its parameters is determined by multiplying its learning rate by the derivative of the slope. So if the derivative is negative, it takes a step down.
But the terrain of a massive neural network isn't a perfect, smooth bowl.
Not at all.
It's full of ridges, bumps, plateaus. So what happens if our marble rolls onto a completely flat plateau, but it's high up on the edge of the bowl?
Well, the slope flattens out, so the derivative hits zero. F prime of x equals 0.
The turning point again.
Right. And in machine learning, these flat areas are known as stagnation zones. This could be a local minimum, like a shallow crater halfway up the mountain, or maybe a saddle point, which looks flat from front to back, but curves upward side to side.
But if the math tells the AI the derivative is 0, and its step size is calculated by multiplying by that derivative.
Yep. Anything multiplied by 0 is 0.
Wow. So the AI's physical step size literally becomes 0.
The automated performance optimization completely stalls out. The mathematical trigger to keep updating the parameters has just disappeared. The algorithm registers that it hit a turning point and assumes it has found the bottom of the entire multidimensional space.
Even if the true minimum, like the best possible performance, is just over the next ridge.
Exactly. It thinks it's done.
The system is completely paralyzed by the math. It hit a critical turning point prematurely. So how do engineers prevent a billion-parameter AI model from just getting stuck on a flat spot and giving up?
It's a huge problem, but they alter the optimization algorithms to basically simulate physical momentum.
Momentum?
Yeah, modern optimizers, like one called Atom, they don't just look at the slope directly under the marble at that exact millisecond. They factor in the moving average of the past gradients. They give the mathematical marble mass.
Oh, that is so clever.
Yeah.
So if the marble rolls down a steep hill and hits a small, flat plateau, its simulated momentum carries it forward, rolling it up and over the ridge so it can find the true downward slope again.
Exactly. They're engineering ways to push the system through a false f prime of x equals 0 state, just so the algorithm can re-enter an interval of strict decrease. Getting trapped at a zero derivative point is actually one of the most persistent challenges in training advanced neural networks.
It's honestly fascinating that a cutting-edge artificial intelligence running on clusters of supercomputers is ultimately at the mercy of the exact same calculus rules as a roller coaster at a theme park.
It highlights the universality of these principles, doesn't it? But it introduces a massive practical paradox for engineers.
What's that?
Well, AI models have millions, sometimes billions of parameters. Aerospace models process millions of fluid dynamic data points, and calculus is the mathematics of smooth, continuous curves. But computers, they don't understand smooth curves.
Right. A computer processor only understands discrete binary blocks of data, ones and zeros.
So how do you use a discrete machine to find the perfectly continuous, mathematically exact moment where a derivative equals 0?
Right, because engineers aren't doing this complex algebra by hand on a chalkboard for months.
Yeah. No, of course not. They build automation engines.
And this is where we bridge the gap between pure mathematical theory and applied modern engineering.
Hmm.
And it usually happens through Python.
Yeah, Python is the workhorse here. The standard workflow for tracking these monotonic intervals relies on a very specific computational stack.
Okay, lay it out for us.
It usually starts with a library called SIMPy, and unlike standard calculation software that just approximates numbers by crunching decimals, SIMPy performs symbolic computation. It evaluates the math analytically.
Wait, symbolic computation. So if you feed it a complex, continuous function for, say, aerodynamic pressure,
Yeah.
it doesn't just guess points along a line.
No. It treats the variables algebraically, like a human mathematician would. It does that to calculate the absolute true roots where the derivative is exactly zero.
It preserves perfect mathematical precision. That's incredible.
It really is. And once SIMPy identifies the exact boundaries of those intervals, those exact algebraic turning points engineers pass those parameters over to libraries designed for numerical data.
Like NumPy.
Exactly. NumPy handles the heavy numerical lifting. It takes that perfect symbolic math and translates it into discrete numerical arrays that a computer can rapidly process.
It maps out the state profile.
Right. And then a visualization library like Matplotlib takes those discrete arrays and renders them graphically. It actually plots the exact regions of strict increase and strict decrease on a screen.
It takes the invisible theoretical calculus and turns it into an actionable blueprint. So an aerospace team can literally look at a monitor and see a red boundary marking exactly where max Q will shred the rocket if they don't throttle down.
Yes. Or a machine learning researcher can look at a loss curve and visually identify the exact plateau where their model's momentum died.
Software essentially acts as the translator. You define the physical parameters, the software handles the analytical derivatives, and the output is a map of the physical or computational reality.
It gives engineers the ability to see the invisible rules governing their designs.
It's amazing. We started today with a textbook definition of monotonic intervals. A system is either scaling up, decaying down, or momentarily suspended.
A simple concept.
Right. But by unpacking the mechanics, we've seen how that one rule dictates the immense physical stress of a rocket hitting max Q. We've seen how electron crowding creates opposing intervals of voltage and current inside just a simple phone charger. And we've mapped the multidimensional terrain of an AI trying to avoid being paralyzed by a zero-derivative saddle point.
It just proves that foundational mathematics isn't just theory. It scales across every physical and digital domain. The underlying rule never changes. Only the material it's applied to does.
Understanding this principle, just knowing the difference between climbing, falling, and stalling, is like having a skeleton key. Once you can visualize an interval of increase or a critical turning point, you really understand the secret mechanical language of the technology all around you.
You do, but, taking a step back from the engineering and the code for a second, there's a broader dynamic at play here, too.
Ooh, where are we going with this?
Well, in every single system we discussed today, whether it's the physical peak threatening a rocket's hull or a neural network losing its momentum on a flat plateau, the most dangerous, most defining moment is always when the derivative equals zero.
The turning point.
The turning point, the moment of suspension before the trajectory shifts.
Right.
So if every complex system, from orbital mechanics to artificial intelligence, is defined by these critical turning points, how might we look at the non-mathematical system in our own lives?
Oh, wow. Tracking our own intervals of increase and decrease.
Exactly. I mean, we all go through periods of strict increase phases of rapid learning, career growth, scaling our own efforts.
And we definitely experience intervals of decrease, too.
We do. But if we analyze our own trends, the real challenge is learning to anticipate our personal critical boundaries. Can we identify our own max Q or our own stagnation zones before our personal derivative hits zero?
Can you recognize when you are suspended right at the top of the roller coaster before gravity decides which way you're going to fall?
That's the question.
You might not have an automated Python script to graph out your life's trajectory, but you can certainly learn to feel when the slope is changing beneath your feet. Keep an eye on your intervals. Thanks for joining us on this deep dive.